phase currents, which is pretty good. We'll modify it a little bit.
Shall I?
Yeah, go for it, mate.
Okay. Thank you, James, and Claudia for organizing this. My presentation is a bit long, so I hope you are getting strong with this as our food. You will need it. I hope the presentation is gonna be useful and not just full of math. Today I wanted to talk about more what we are doing rather than more what we did. I know you probably might have a ton of questions about what we did, but I just wanted to show you the new stuff where we are going. So, but before going to, that math, so let's just, by the way, we will start recording.
Yeah.
So, what I wanted to talk is how I see motor intelligence. It's a combination of planning and understanding. And reasoning is a process that will involve both planning and understanding, as I was saying. So here I'm talking about motor reasoning. So you have the robot have a task to do. It's tasked to pick this object and bring it to another place. This is the kind of intelligence we are talking about here, the motor intelligence. And I don't know what's happening, but my computer is not reacting. Yeah. So, understanding is a process where a robot have an idea of what is happening around it, and rather than planning, that is making some decision. And here you can see our go-to robot is carrying on a payload, and he doesn't know about the payload properties. And if you don't know about the payload properties, the video is not playing well. Sorry, I don't know why. So actually the robot struggles to work. And one caveat in robotics, we need to do all this in real time, otherwise it's useless. So this is one of the big challenges we have in robotics. We need to solve very complex problems in a matter of few milliseconds. So we need to understand, to plan. Robots need to understand and plan. And there are different ways to do it. One way we work a lot, but doesn't mean it's the only way, and I believe it's the only way, and it should be the only way. I don't believe it. But what we have done a lot is what I call top-down approaches, top-down perspective. So planning, you can formalize using optimal control, and it passes this problem of making decisions in terms of what is our goal, how can we achieve, and which factors ensure that task. In step understanding, the way I see is you can formalize using optimal estimation framework. It facilitates the robots to, be an understanding based on things like what are our belief or the robot belief, how we can interpret the observation, and which interpretation are feasible or make sense. So the way that I see, again, this is one perspective. I don't want to sound that is the only perspective. The way that I see is that these two guys are actually building blocks for motor intelligence. And they are actually based a lot into physics and optimization principles. So first principle. And yeah, with third principle, you can do things like we show in this video, we see this video. So a robot can navigate through over constraining environment and robotics. With constrained environment is quite clear. So you have to navigate over an environment where you have a few options, in this case, for making foot step, but constrained robotics is when you have a robot that to achieve that, they have to deal with their own capabilities in terms of actuation and cannot be neglected, let's say. And this video shows actually both. What I like a lot about the down perspective is because they bring a structure. And I think a structure is all you need. And this is a strong claim, so please be nice with me if you disagree. So people talk about attention, but actually I see attention as a way of a structure. But it's, an empirical structure. So in motor decisions, so making decision, understanding decision, we know pretty much what are the structures. And that is pretty much understood when you study the two algorithms. We are building a set of foundational software, and you know Crocodile, so it's open source. A lot of people is using it. And it has been a nice success, but this is something that you probably haven't heard. Let's say a few of you. Caracal is basically, let's say the MVC formulation, and Crocodile is its backend. And when you see all this experiment in previous research, all are wrong with this guy, Caracal. Now, this is what is actually done, and you probably are aware of this, but we are building two more foundational software that are still private. But yeah, somehow really cool projects we have working. So the first is Audit, it's an optimization framework. And the second one is Genesis, it's a simulator that we are building. And a lot of my presentation will go here because Odin is actually the backend of Crocodile, but also the backend of Genesis. And I believe that could be the backend of many things like RL training policies. So let me focus a lot on optimization, and this is where it comes, a lot of difficulty. I will try to be, easy to understand, but for optimization is actually a language. That's the way I see it. It's a language for formulating, for example, and solving decision problems, making decision problem, understanding, and so on and so forth, even the learning processes. So actually, I think optimization is fundamental to understand, and I think hopefully you will enjoy this part. But optimization, what you have to do is to optimize some function F. So that's your metric. That's what you want to minimize, but you are often subject to different type of constraint. And we like to make a distinction between type of constraint because it's important in the way we solve it, and you will see in a minute. So you have equality constraint H and inequality constraint G. And these mathematical objects, these functions can be nonlinear, linear, and then there are a bunch of different categories of optimization depending on how they are. H can be typically it's a continuous, but it also can take integer values. I will focus just on continuous because I don't think there's so much to do. And you have an example. So the cost function defined is cost landscape, and then you're subject to that gray region, and then you need to pick your optimal solution at the start. So as I said before, a lot of algorithms can be boiled down into this formally. So you have model predictive control, moving rights estimation, context physics, and who knows how much of them. But it's not only model-based control, also in model-free or other processes like reinforcement learning, behavioral cloning, physics-informed machine learning, etc. So I will focus a lot here, where a lot of my career have been done, but doesn't mean there's nothing interesting on the other side. So the way we solve this problem is first we have to find the so-called KKT condition. The KKT condition are conditions of optimality. If you met them, you found the optimal point. And there are different. The most important is the first order necessary condition, fund or form, for optimality. And we will typically the way you do is you formulate this Lagrangian function where you have f and then you have the multipliers y and z, and that are basically your Lagrangian function, and you use the first order necessary conditions to actually build this type of feasibility. This is a dual feasibility, so you're saying basically that the Lagrangian of that function, the gradient of the Lagrangian of that function has to be 0. It's kind of easy to understand. You have a function, you are in the bottom or in the top, depending if you're minimizing or maximizing. And then what is less obvious, but I don't have time to go through it, is you need to certify that the multiplier is positive. Actually, the Lagrangian function is an approximation of what you want to do, and the field to understand this is variational analysis. So now this dual feasibility is a set of nonlinear equations. This dual feasibility, you know, do the math, you get that equation you can see there. So you are getting the gradient of x and etc. So obviously the multipliers doesn't depend on x, so that's why we don't differentiate them. And then also we have the primary feasibility. So it's kind of obvious as well, are the constraints you need to satisfy. So you at solution, you want to satisfy those constraints. So you have a point that satisfies those constraints, and that's called primary feasibility. And the huge complexity you have actually in optimization is dealing about complementary flatness. And the complementary flatness is basically deciding when you are activating a constraint or not. So you basically have a multiplier that multiplies element y. This is the Hadamard notation. A constraint. One of these has to be zero to be satisfied, and it's a way to define activation. And dealing with that complementary slackness is really challenging because this is a very nasty function. And I'm going to talk about this. Now, you got these feasibilities you want to get, but these are all nonlinear equations. When we talk about nonlinear programs, if you have and when you have nonlinear equation, the way to find the roots, which are the KKT position, is by using the Newton method. By the way, there is also the second order sufficient condition that basically, if this equation is positive, it's telling you that you are descending always. But that's all. And I went a bit, so I want to focus just first on explaining how to derive the KKT condition for equality constraint, and then I will go for inequality. So in that sense, we will build up our knowledge in the most easiest way. So we said that we want to find the roots of that system of equation. And then the way to do this is using the Newton method. That's basically the Newton method we have. And when we plot that Newton method, we get the system of equation. Typically, we call this the KKT system of equation. So what it does is you want to factorize this matrix in such a way you can compute these deltas. So, and those deltas are typically called the zero direction. So the days that you need to be closer and closer to the optimal. And you need to do this iterative. As you can see here, this part here is our R vector. So the residual, dual and equality or primal in this case. Then we want to see how it works with inequality constraints. So, and one approach that is predominant is the interior point method. Although it's not greatly used in robotics, and you will see why. But interior point method is probably what you have used when you solve one of these problems. I thought K-neutral all are based on Gurobi or are based on this interior point method. Now, when you, as I said before, the complementary flatness is the problem here, is the difficulty. And because you have this shape here, either you have G activated, so it takes a positive value, or either you have not activated, it means that the multiplier, the value multiplier, it takes some value. So you need to be in this region here, in this kind of manifold, which is not differentiable. And the way you do it, you use a log barrier function. So you can basically, the log barrier is represented by this yellow region here. So you are kind of smoothing because you are now saying that you want to satisfy Z times G plus mu equals 0, where mu is actually the barrier parameter. And you see the log barrier function there when we apply. So building the KKT condition is just taking the differentiation of that and doing some a range of things. So terms. So for example, you can, when you differentiate the log function, you will get that, and you define say I equals to mu minus 1j. So that's the derivative of the log. You can actually plot that and build this residual. So now what you can see is set is a diagonal matrix. and then G is your constraint, and then you have mu. You are basically relaxing this. And the whole idea of the integral point method is solving this sequence of problems where you got one value of mu, and then you keep reducing that value of mu until not zero, but a pretty low value that you can say yellow is actually equals to blue. So then the same story, you build your Newton method, you use your Newton method to build the KKT system equation. This is a nonlinear system equation, and you need to find the root x and z, where z here is the multiplier for the inequality, and you get a system like here. So this is in essence what integral point method does. Again, you need to invert this matrix to compute this z direction and so on. When we assemble this equality and inequality constraint, we have now this new system of equation. So you can now see that you have the multiplier associated to the equality constraint, you have the multiplier associated to the inequality, and these are the terms we just saw before. When factorizing the system equation, you compute a certain direction. So as you can see there, so it tells you how to much, what is the direction you should take to be closer to the optimal. But typically, you need to evaluate how much you will move along that direction. And that is typically done through a line search. And you need to basically figure out what is your alpha value that makes sense. Because you are making an assumption here, or you are taking a certain direction based off a linear word, although your word is not linear, and then that linearization might hold in a region. That's why you need some kind of figure out some kind of how much you will move along that line. That is the limit, and you need to use a criteria that is basically evaluating that you are making positive improvement. In the context of DDP or even deep learning, so this is what we call the backward pass. So, and this is what we call the forward pass. So what is beautiful is that everywhere you have these forward and backward passes, and basically the forward is simulation or rollout of your system, and the backward computes the sensibility. And again, deep learning also have that, and this is pretty common because in essence there, when you use ADAN or a stochastic gradient descent, in essence you are solving a type of optimization problem. So now I want to do a brief description of the families or the challenges of optimization and why optimization is not a finished field. Actually, there's still research going on, not necessarily in our field, but in other fields. So why optimization can be challenging? Well, you can have problems that are degenerated, ill-posed, and large. So degeneration can come in a form of linear dependency. So constraint can be dependent. So if you see, we have to factorize a system of equation, and that requires some Jacobian, and that means that the factorization, the metric you need to factorize, is not anymore invertible or is not rank efficient, and so linear dependency will bring that. So there's another thing, you can have not uniqueness in dual solution, actually also in primal. So problems can have multiple solutions. And so how you have an idea of that when you solve inverse kinematic problem, you know that from experience, but the not uniqueness is not only the primal. So in our vector that we want to optimize, but also in the duals. And you might have singularities in the Hessian, so things like that. And these are all challenges, all challenges that we know about optimization. And you can have things like a small constraint violation or near zero multipliers, cast instability, or ill conditioning. Ill conditioning refers to a matrix that where you take their eigenvalues, the ratio between the minimum and the maximum is large. So it means that it's very sensible to some directions where you compute and pose numerical challenges because we are solving this with numerics and not in paper. Now, the family of optimization algorithms, I just introduced integral point method. And I just said that is the warehouse of modern numerical optimization, especially for large scale optimization systems. They really shine when you have a large number of inequality. I'm not claiming this. This is known. But it's one of the kind of might look nice, but actually is horrible, is that they might maintain a strict visibility of inequality constraint. That's how comes his name, interior. You need to be always in the interior region of the inequality set. And that poses challenges when you work start, and in robotics, we have to make decisions every millisecond that are similar to the previous one, slightly different. And then you want to reuse the previous solution. You want to warm start the solver to speed up. And then again, warm starting is a huge problem. And that's the reason why interior point will never be useful in robotics or AI that you have to make, or any process that you need to continuously solve optimization problems that are slightly similar. And you want to warm start.
Quick question, is a way of circumventing that, like the use that you have of the slack variable view under log barrier functions, if you just start?
If you have a slack variable, I actually was going to introduce some strategies that those are, if you have a slack variable, you still need to certify that the slack variable is, for example, positive or negative, and that you still need to handle that inequality in a way. An interior point will be the barrier, and because they are in the interior region because you use logarithmic function, and you know the domain is just in the, we call the positive order for the log function. In other words, it's within the region, if we say that. But I mean, I think the slack variable is just moving the complexity from one place to another. Now, how you solve inequality with interior point, with augmented Lagrangian, with something else, and I'm going to show you about something.
Okay.
The good thing is they have locally quadratic convergence. That's why the power, the work powers, and also because so large system of inequality, system with many inequalities. Now, more recently in robotics, and I think also AI, so a lot of people have started investing in something called augmented Lagrangian method. They are not new. They have the seats. They are as old as interior point method. And this has happened especially in the last decade. And because it has some features that renders attractive to robotics. So instead of using a barrier function, you have a penalty function. So it means that you don't have, you can pass you can warp start outside the region. Augmented Lagrangian actually was historically developed for handling equality constraint, not inequality constraint, and actually they excel in handling that because they can handle nicely random efficiency. So imagine when you have your data straight, you want singularity, that matrix go random efficient, you need a solver to handle that. A lot of people in robotics circumvent like, okay, I'm gonna bend my knee. But yeah, we know that bending knees is not the optimal way of working. So this is the feature that renders augmented Lagrangian nice and people developing because you don't need to certify a strict feasibility, and actually certifying a strict feasibility every time is not really good, although it might be counterintuitive. So it's good for warm starting. However, it's super linear convergent, so it doesn't converge as fast as interior point. And it actually needs a lot of well-choice decision on how to select estimates of penalties. So that is where the difficulty when you have to implement one of these algorithms, they are high sensitive to that. Now, so I'm going to start talking about our solve. And I'm going to start talking about Odin. And Odin, what is Odin in essence? It's an odd system. We'll see what that means. A non-interior point, which we also see what that means for quadratic programming. And actually, what we have developed for quadratic programs can be extrapolated to any type of mathematical program. And we will probably next year work in a second order program. So, so at the time being, it supports dense and sparse backend. And let me explain what I meant with this, or what we meant in optimization. So you have this quadratic program. So it's a program that have a quadratic cost function and then linear constraints, you can see there. And when we say that it's dense, we refer that the matrix Q, A, and G are dense matrices. And when we say they are sparse, so you have some blocks that are zero. Now, one thing that I learned in my career is that matrices are mathematical objects and not just numbers. So they have a structure. And that's something obvious for someone working optimization, but sometimes for us in robotics, it's not that obvious. Now, here, before talking about the solver involved in that journey, I just wanted to show you some results. So we took the Maros-Mesaros test set. So this is this was proposed by these two folks, Maros-Mesaro, I think 2 decades ago, something like that. And they have many QP problems standardized. They are the hardest problem you can find. So it's the right way to test your optimization idea. And you can see some of the solver we consider outstanding. So you have ProxQP developed by Justin Capetin, one of my ex-colleagues at Agile. You have PyQP. ProxQP was developed 3 years ago. PyQP developed a year and a half ago. In EPFL, those guys are doing optimization. OSQP, probably you know it, was developed in Oxford and was developed by optimization people, not robotics. And then we have Mosset and Grovic, probably you also know it. These are commercial solvers. And you can see that we took all these solvers, all these problems, we solved 90 problems, and almost as Grovic, which solves 93. And if you pick the ones that are done by others, like ProxQP, and it solves 69, and OSQP, which is probably the most popular QP solver, it just solved 58. So OSQP is already deprecated, although a lot of people use it because it was developed 10 years ago. I have a long history. In essence, ProxQP is a prime and dual augmented Lagrangian. PyQP is a prime and dual proximal interior point method, so not useful for robotics. Let's say I don't care. All is good, 92 like us, but not useful. ADMM like it's OSQP. So it's like a family of augmented Lagrangian. And then you have Mosset and Grovic, which are, as I said before, commercial, but again, interior point method. So I don't care really. Don't need it. I cannot use it. And so I just really care this somehow, because these are my competitors in robotics and AI. However, we want to see how well we can start our solver and compare them. So here we have a plot where we pick these 2 other solvers. Odin is blue. And what we do here to generate this plot, by the way, we use a method that has been proposed to validate one starting. So what the method consists in following. So you solve one QP problem in that format. And then what you do is you randomize Q, C, A, B, G, H. You randomize. And then you solve that problem and use the previous solution. In essence, it's like when you are solving a whole body controller, so your next QP solver will be slightly different. So in essence, you can see as similar with some randomness. So that's what we are doing. And then we compare what is the ratio between the number of iteration when with this problem. So a low ratio means that we are not adding so much extra iteration. It means a plot that is going low, and a high ratio is you have a plot up in the top. So you can see that in both type of plots, Odin is actually much better than all the solver. So because it requires less iteration to solve, and I'm going to show you an example towards the end of my presentation in the context of simulation. And between this plot and the other, we have randomized more this one here. So it's like it's more random and it still keep a same shape. While you can see that, for example, Prox could be start struggling. So when you are farther, struggle more, quite obvious, but in our case, it remains similar. So I really consider this an outstanding result. So now let's talk about how we managed to do this. And we are actually blending kind of primal dual interior point method with augmented Lagrangian in a way that is unique and leads to a non-interior formulation. So before explaining the algorithm, I need to explain some insights because we are not an optimization room, so we need to have some insights. So let's focus again for inequality constraint for a minute. So you have that QP problem with only inequality constraint. We do what you were saying, Robert, we add some slack variables. And that's what it does really in essence, is to move the inequality constraint complexity, because now your inequality constraint GH, blah, 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 becomes an equality, and then you have an inequality in S. But still you have to handle that. It's much easier to handle, sure. And now what we do is we introduce something we call consensus variable. All these are artifacts to build a new idea. We don't optimize those consensus, just to be more clear. Variables, and that's what it held up, is to isolate S with she, and we will see why. So we want to do this. Now, if you apply interior point method, so you want to build a log barrier function of she. So is that yellow term? And now you have formulate something that is a inequality constrained problem into an equality plus some cost that penalize the inequality bits. So that log barrier function is actually blending interior point method, but we don't stop there. Just so what we do is we start adding some kind of quadratic penalty function to relapse the interior point condition. What I meant, if we go from that problem to the other one, so where we are adding this quadratic penalty that is relaxing this kind of, condition, consensus constraint. We call that consensus constraint because S and she can take different values. And then, and this can be seen, again, it belongs to a primal dual augmented Lagrangian, because that is kind of an augmented Lagrangian there you are there. We can build a Lagrangian function. So I hope it's much faster to go now, but you have first the function here, f, they want to minimize, then this low barrier, and then you have, the thing associated to the equality constraint or inequality constraint that is transforming equality constraint, and then you have the constraint associated to the consensus, and then you have the quadratic term. So this yellow is what we are adding new, and when we build the KKT condition, we have that system of equation here. So again, dual residual, primal residual, and these are new guys that we are seeing here. And this is the derivative with respect to she of the Lagrangian, and this is the derivative with respect to S. I mean, maybe I can just skip, but if you want, it's very easy to figure out that.
I'm having trouble seeing how the objective function that you have for minimizing the difference between the slack variable and the other thingy, the she variable, is not redundant with the quality constraint. So, because like if the quality constraint says that they're equal, wouldn't that impose that the cost?
Yeah, it is kind of redundant. It's kind of redundant, but so I think it's not clear at the time being why I'm doing this, and I really apologize. But if I go to the slide
later that
yes,
so as to why you need that.
We are doing some kind of artifacts here. It's not really obvious. It took us some time to get it, but you will start to be obvious. So there's kind of redundancy. Yes, I've said that point. But when we do some trickery, you will see how things change. Just give me more slides, or probably a couple of slides. So now you have got that KKT condition, but if you see this is a second order equation, and the beauty of that is you can solve, you have a closed loop form solution of that. That's the beauty. So you can rewrite that equation, the yellow as the other term, and you don't see it's a second order equation. Now you see little dots is because we are using a Hadamard notation, so it means that for each inequality you have this type of second order equation. So, and now we know that analytical solution actually is a second order polynomial. There are two solutions, but we pick ones. And the one that satisfies G equals positive. And maybe things start to be more obvious. So this is a solution of the that we pick of that system equation, analytic closed form solution. And then when we plot it back into that equation, we get this system of equation here. Now we got rid of G. G is not anymore there. Bye-bye G. And we got this function there. In a minute, I will explain what this function is. But basically, this is a trickery that we do. And that function, it's called a smooth minimum nonlinear complementarity function. The minimum non-complementarity function is defined by this, is basically why it's called any nonlinear complementarity function, because at the root of this equation, you got the complementarity conditions satisfied. And so you got that your flat variable is positive, your constraint, and then your multiplier is positive, and they are multiply equal 0. So this is, think about in terms of context. So you have S is the sign distance function, Z is the force, and then those guys that multiply are the complementary slices. So we start working with NCP just because we saw a lot of potential in context physics. So that's how we arrived here. But we wanted to validate this in a numerical optimization algorithm before going towards a simulation. Now, an smoothed version is the version that is parameterized by mu, and then you have a smoothed complementarity slackness. So that mu is smoothing. And there are different types of NCP, and there are papers that talk about this. One of the most predominant, everybody talks about it, and probably if you hear about NCP, probably you hear about this, is the Fischer-Bullmeister. And it turned out that the minimum function can be rewritten as the Fischer-Bullmeister. If we do a little bit of math, though, we go from here to here, and then we know that S times Z is equal to mu, so we can replace it here, and then we end up to this form, which is the form that you find when you research about Fischer-Bullmeister NCP function. So in short, you can write your residual like this. So NCP, and now if I plot I do a 3D plot of the NCP, you can see that it includes not only the positive orthan, like a log barrier function, but it also includes a negative orthan. It means that I don't need to warm start within the interior region anymore. And that's why we call it non-interior methods. And when we build the Newton method, we get to this system of equation here. So it's basically taking the derivative of that. You get this derivative with respect to Z and S, and then you get that residual. So that's how we go from non-interior, from interior to non-interior. That's how we go from be able to not be able to warm start to warm startable solver. And this is basically the main idea behind our solver, but our solver is way more complex like that. I just wanted to bring a key insight before throwing those equations that are actually quite complex. So now I never say that, but I want to take the opportunity. So for me, interior point, because relaxed, is the right tool for handling inequality constraint. And a lot of people that does augmented Lagrangian, what they do is they project within the region every time. And that projection can be seen as non-smoothness and destabilization of optimization. And that might also explain why our solver is much. It's almost like an interior point method, but with more startable. So I pretty believe people is doing wrong.
I think that's a really interesting. So you're saying that by doing the projection onto the constraint surface, as opposed to doing like your line search and the updates, you lose the smoothness of the line search aspect. And you think that that smoothness actually helps with the ability to basically
Yeah.
get to a solution as
Yeah.
opposed to having that step change causing an instability?
Yeah, and also I'm gonna go further. When you differentiate copy solvers, which I'm gonna talk, you want to differentiate because not as smooth, it means it's not differentiable, but it also means you have some gradients. So you have a set of gradients, in other words. And the set of gradients, you have to always, when you do non-smooth optimization, you have to pick one of these. But you can pick one like this in this direction, and then suddenly you pick this. This jumping gradient. It's like the gradient is like a motor. Let's say, please do that, and then next day you ask the student to do another thing. So destabilize the student. Same in optimization. So people is doing that, but I think it's wrong, fundamentally wrong. And this goes profoundly not just to solving QP, but differentiating QP, so you can embed QP layers in the learning. So, but we will go there. So maybe I will try to speed up a bit this part, but what is really great for augmented Lagrangian is handling equality constraint. And that's how I start to feel, to be honest with you. They are extreme, and that's how we should use them, not in the way people use it in augmented Lagrangian. So let me focus on equality constraint and explain what are the problems. So when you have a Q matrix, I mean, to be able to invert that matrix there, so which is the KKT system that we just saw before, this matrix here, well, you need that this matrix is square and invertible. And to achieve that, you have to observe that Q has to be strongly convex. That's how we say in optimization. In other words, has to be positively defined matrix. And A has to be full rank or met all these linear independent constraint qualification that I mentioned before. And if the problem or the matrix is ill-conditioned, so you have a bit ratio between the minimum eigenvalue and the maximum, so it's ill-conditioned, it's furthermore quite challenging. So a trivial solution we use a lot in control is use the Selden inverse. But Selden inverses are not an option and no one do it. And actually are horrible. Every time I avoid this. And I'm going to explain why I avoid in my life. I never use Selden inverses until I learn. Yes, yes. So numerical instability. If Q and A are conditioning, it's difficult to set what is the rank of that matrix. And Selden inverse, what it does, it computes eigenvalues, so do a set singular value decomposition, and then say, well, the ones below this threshold, a number that is pretty close to zero, they are zero. But might happen that some problems, some matrices have near zero eigenvalues, but they are wrongly classified as a rank deficient. So that's a problem, and that's happened when you have ill-conditioning matrix. So when this matrix Q and A are kind of plastic, so it produces no numerical instability. It's have a poor globalization. I'm gonna explain you this in control terms. It is a one-shot projection, so we know that Selden inverses project, and that means it's too restrictive and too risky and poor globalization. So it is like a feed-forward control command. So you compute, you have the perfect dynamic, you compute it forward there, forget about feedback. You know, I'm a Purist person, I want to do feedback, but when I put that, it doesn't work because your dynamic is never perfect. Because even in a simulator, you discretize the dynamics. It's a proxy. So the same is kind of this one-shot projection is like a feed-forward turn, and you require some kind of feedback. And augmented Lagrangian brings that feedback. So they are expensive to decompose because they use similar value decomposition. The most expensive one, horrible, inefficient. So, and there is no guarantee of convergence because that projection. So therefore, if you can avoid it, I mean, in numerical optimization, we cannot have that loser to not avoid it, but yeah, somehow, sometimes if you solve problems that are well understood for narrow, condition, you might probably tell them that can be okay, but it still would be expensive. So the way to this, what I was talking about is all about degeneration in optimization. And the way to post something that is degenerate is to regularize, to go to regularity. That's how it's explained in optimization. Sometimes it doesn't take time to understand what they are trying to say. So proximal point algorithms introduce that regularity by adding constraint penalty, quadratic penalty, sorry. And that's avoids also the need to have a strong complexity, so that Q can be semi-defined, positive semi-defined, doesn't have to be, even Q can be zero, if I'm honest with you. And also ill conditioning by shifting the constraint. So what in essence does augmented Lagrangian, and Rockefeller is your guy, if you want to understand about this. So what in essence you do is you add these quadratic penalties that you can see there, and you have this, now I'm introducing something called E. XE is the estimate of X, and Y is the estimate, YE is the estimate of Y, the multiplier. So that basically is like you are kind of adding regularity because you no idea, you were estimating, okay, I want to be as close as possible to my estimate, is kind of the regularity you add. And this, the most recent way of doing this, actually, someone in 2012 bring this view. That's a paper for I think not for people. So bring this view that you can generalize augmented Lagrangian. So proximal method, ADMN, proximal point profile Lagrangian, even quadratic penalties are all being classified as augmented Lagrangian. And you can classify with this equation here, and you just need to change the parameters rho e to have different views. I'm not gonna really go through much onto that, but it's called off-shifting because what it, in essence a quadratic penalty does is like shifting your constraint. So now you see a shift in the constraint here. So a quadratic penalty is like a PD controller. So you increase the quadratic penalty, you get closer to your reference, but you need to increase towards infinite to be there. But if you do that, it doesn't work, right? Same in optimization. If you do that, what you have is an impulse with conditional metric because you have some values that gets really massive. So quadratic penalty is not the way you want to go. And the estimates, if you got a really good estimated, you are kind of shifting. That estimate is like a feed-forward term. So you want to keep a quadratic penalty small and then an estimate really well. So that's pretty much what you do.
Very quick question for like linear programs. If you run into degenerate solutions, is there any, like you couldn't add a regularizing term for an LP? Is there like some other method that might be applicable there if you can't apply like a quadratic penalty to regularize?
Yeah, you can apply a quadratic penalty to regularize, but that's actually what we do when we solve linear programs. And I'm gonna show you something about this. We do a kind of regularization, but the regularization that you put as a user to the solver is not the same. It's not that the regularization that internally the solver does. And I want to emphasize this because I know some people might get confused. When you add your regularization, so when you want to solve a linear program with a QP, and the QP is not that advanced, you regularize, you add a small row time identity. But that problem is not anymore a linear program, it's different. The KKT condition changes. So the optimality, the optimal solution is not the same. The smaller is the regularization, closer you are to the optimal solution. But with the internal regularization that the solver does, it solves the real problem. It's just it progressively making it like nicer, regularized, but at convergence, you solve the same KKT condition. So
So you're saying, yeah, you're saying you could use this whole framework to solve an LP and all the same stuff.
yeah, to solve an NLP, yes. So we are working to solve DDPs with this framework at the moment, and I'm gonna talk. But yeah, so this is more or less when you regularize, you have your KKT condition plus some yellow term. That is called perturbed residuals. So because you are, if these two guys are equal, well, this is 0, same here, then you are not perturbed. So then it means that you have the same KKT residual, and a convergent you got, indeed a convergent H and HE are equal. So yeah, that's kind of explaining why you are not, it's not that, when you do your regularization, you are not having something like this, like trying to estimate. So you have always a term here that is changing the KKT, the original KKT condition blue.
Carlos, when you're adding that diagonal matrix to Q on the left there, that's essentially what's making that slightly convex and like red.
Yeah, that essentially is making the matrix nice, invertible. Yeah, that's correct. So now these are the key insights, and now I'm gonna go through the ideas we brought, the novel ideas. So in interior point methods, you have something called centering procedure. So you want to have more or less that inequalities are violated more or less in the same way. So in that way, your matrix is well posed. So it's called centering. And the really well famous approach to do that is called MPC, not the MPC you know, guys, but it's Merotra predictor corrector algorithm, and basically centering that. So we don't do that MPC approach, but rather what we have is a kind of a smoothing parameter, and then we are computing this kind of surrogate of measuring complementarity. So it's kind of telling of how unbalanced it is, and we want to balance. And then this, if you see from the previous, if you remember this log with transforming an MPC, basically is a way of regularizing the NCP. And yeah, that's happening every iteration is changing, and we have some rules that to change this smoothing that I'm gonna prefer to.
What is the picture that like you should have in mind for centering? Is it literally just like trying to find the middle of the inequality set?
So it's trying to have all these sigma more or less in the same value. So when you invert it, if you have, remember that we need to build the Jacobian of this, and this go to the KKT matrix, and you need to invert it. So it means that is going to be a diagonal matrix, and the values of those diagonal values terms will be roughly more or less the same. It means that the conditioning of that matrix is nice. So that's why you need to center it in essence.
Right.
But
does that not map back to like anything to do with like the interior point?
The interior point
formulation at all, because I had in my the picture I had in my head that might be wrong is that you've always got to remain inside this inequality set. So to keep everything like well conditioned, you'd almost like stretch out axes of the problem such that you're always in the center. But I mean,
in interior. I mean, you can implement an interior point without a centering procedure, but that would be like a toy implementation, not a serious one. So interior point methods typically use the Merotra predictor corrector, but the Merotra predictor corrector, you have to read about it. I'm not explaining, but you need to factorize twice the KKT matrix. Is expensive. Here you see it's just a few rules. Like this is basically couple of if to obtain this smoothing, and this centering procedure is our novelty. In short, no, that's everything here is quite novel. So no one really has done something about this like this, and everything that I'm talking about here. So now we have all shifted. So basically, I'm just putting all together, and that's how these matrices get beat, and but what we are doing as a novelty is like we're shifting this, like adding regularity in the let's say in the complementarity slackness. So this is what it's doing. Remember that you have something like S times W equals 0, and that now I present S times Z, but W is actually the multiplier of the consensus, which should be equals to the multiplier of Z at conversion. So I haven't really explained that, but you can see the equation here. So the multiplier. So that maybe explained it.
Why the cross?
And this is this regularity. Let me explain this, and then this regularity is quite unique, and no QP solver have it. So it means that you can solve. I was talking with you before. You can solve problems where you are touching the surface, but no contact force. So when you have both the constraint and the multiplier both 0, those problems are madly difficult. And you can find even in physics. Corner cases where you just touch but no force. In optimization, you can always find this as well. And yeah, this regularity is essential to solve those problems. And so far, we haven't found a solver that can solve this type of problem. We have this type of problem identified, some of them, and yeah. And I think this all shifted NCP function is quite relevant, and it's like a combination of non-interior or interior. Is blaming non-interior with also augmented Lagrangian, because as I said before, augmented Lagrangian can be seen as a shifting constraints, and yeah, this is like shifting a bit the NCP.
What does the cross term at the end? Like I get obviously, you know, the quadratic penalties on the multipliers S and W. What does the cross term between the multipliers
Because we want to shift in that way. So this is a complementary slackness. So you get these two guys 0, this 0, and everything 0, you will get basically S times Z equal B, which is our regularization. It was the mu that I used before, but now I'm embedding the centering procedure that I just talked. So that's why I'm not using mu here. But we wanted to shift this, and the way to shift this in this way, you need to add those cross terms. So yeah, which is equivalent of shifting it. I mean, if you do the math, you can go from here to here. Where here I'm using vector, and here I was talking about one scalar, but yeah. So is that the type of shifting we are doing? Yeah, I was saying that what I said before, that this regularity allows to handle this type of problem. And it's novel. And this is basically the residual is just adding these terms. So, and then solving a system of equation like this, when you are regularizing here, the Jacobians of the NCP. And yeah, we say that we are perturbing the NCP residual. So we can do the same, I mean, shifting or perturbation by embedding the proximal point penalty on Lagrangian function, which basically leads with this is a system of equation we saw before, this NCP Lagrangian, and this is the shifting. So it's kind of the shift that we just talked about when we talk where I was explaining some of the key insights with augmented Lagrangian. And now you get something like this. Maybe some question are not that familiar. I'm happy to share the paper when it's out, finished. So basically you end up with this system. This is a system we solve every iteration. You regularize Q, but also this regularization are coming from the proximal point method. And these regularization here are again the NCPs all shifting we do. And our perturber residual is like, this is the original residual and this is the perturbed one. And obviously we have some kind of trickery to update the estimate. That deserves some time to also to explain, but I think it's not that useful. So we can condense this system of equation to solve it more efficiently. So it's just getting some row and baby here. I think I'm gonna skip this because there's all other material I want to talk. And then you can embed some kind of Mary function, natural Mary function to evaluate when to accept a step. Remember the line search stuff I was talking about. Basically, so where U is stacking all the decision vector and we have some kind of soft truth region. I'm gonna skip this, so it's not that important.
Just a quick question on it though, not for any details. Is that merit function a merit function in the sense of it will allow the cost maybe to stay the same or increase for the constraint satisfaction to go down?
Yeah, so we accept alpha step when we satisfy this. You can see like a kind of Amigo condition, but we like to call it more like a sort of region because the way we compute this directional derivative. So, and you can see it's a natural Mary function because you want to get this guy 0. When you get those guys 0, you are in the root of the KKT system and you have find your KKT point. Now, I'm gonna go to optimal control. This part will be much easier. Thank you for surviving with me here. I'm sure it was not easy at all what I was talking about. But yeah, optimal control, it's a framework where you, as you know, you want to make a decision in more concretely, specifically, you want to compute a set of control, a set of trajectories, and solve this type of problem that you see here. You have a robot doing some perception and then planning some motion in real time. That's a real time, by the way. So what you do is you minimize, you find controls and minimize, minimize some kind of cost function, and the cost function defines some kind of goal. You have terminal, you have rounding cost. The goal could be put my electrode here, put my sensor there, or just run at this speed. You know all about this. And you have some initial state, and then some dynamics you want to satisfy, some safety you want to guarantee, like friction con, stability, other stuff. So ultimate control is continuous, and we can solve as a nonlinear program. So everything we have learned, we can apply when we do a kind of transcription or discretization. There are different ways. This precision discretization is not the same. But in essence, they put this all these into terms of algebraic equation like that. And that's in essence what both methods do. So you have a infinite, sorry, my pronunciation, dimensional problem because you want to compute all these points, and there's infinite of them. And when you transcribe, what you do is just compute a few of them by discretizing. So the problem becomes finite, it's dimensional. So also is kind of nice to solve. So Bellman, I don't know, one of the greatest American for sure, create this principle that is really resonating after many decades, and it's a principle of optimality. And it says something like, it's a kind of obvious. To solve a big problem in the best way, you solve a small problem in the best way as well, and you combine them somehow. So it's kind of intuitive, but it's profound. So basically what you have is, you want to find your optimal trajectory. So you got this guy and you start finding first an optimal trajectory of magenta, and then you move backward in time. So you split this into a smaller sequence of sub-problems rather than solving the big problem. So Bellman this is kind of upgraded because this is a Bellman equation that is subject to some constraints, like you can see here. Typically Bellman satisfy this constraint every time, the dynamics, and we don't do that because in optimization we don't do that, and actually it's better like this. So if basically you want to minimize a cost function now in your current time B, and then you have an idea what is the value, the cost to go. So it will tell you what is the cost from here to go here. So you basically are synthesizing all this into this little guy, and then you want to choose what is the optimal control here, subject to some constraints, like you can see dynamic inequality constraint. It's upgraded because it's a multiple shooting, so you are not satisfying the dynamics. Bellman is satisfying the dynamics. And why we don't satisfy the dynamics is because from numerical optimization, we know that it's better to keep some infeasibility. It's better to be close to a region of attraction rather than to a region of feasibility, if that makes sense. Because you are computing certain direction with derivative, and the derivative can break infeasibility, but around those infeasibility, those derivatives are more useful than when you want to constrain to be feasible. So it's an upgraded because it's a multiple shooting. In Crocodile, we saw only this at the moment. We don't equality constraint when we do inverse dynamics. And now what we are doing is slowly integrating all the stuff you see before to solve those problems. When we linearize, that problem becomes QP. So it's a locally quadratic program. Now you can start seeing how things connect. So the Bellman equation is the basis of differentiable dynamic programming. So as I said before, I'm gonna focus just in the multiple shot in DDP for now. So not complexity about optimization, this is much easier. So you have this Bellman equation here. What you do is you formulate again your Lagrangian. So for your state y.
What is the circle with the line?
Yeah. So it's a geometrical system. What handles Crocodile? It means that you have a manifold. How to explain it? So when you typically when you have a floating base, you have a quaternion, right? We use Lie algebra, and actually what we are doing is like optimizing in the tangent space of the manifold, and then when we simulate, we graph it in the manifold. And the way that combines, I mean, this notation of a negative, it's like a minus operator, but it's a minus operator that projects into the manifold. So think it like a minus.
Say, if you have like two quaternions, two 4x1 vectors, right? You can't just add them together. That's not how rotations works. You actually have to do the rotation addition. So it's this fancy math way of writing.
Yeah. Some people use a square. I like circles because I'm more, you know, in the Asian culture it's a perfect. But some people use so, but yeah, I hope that that question was sorted out. So you got this Lagrangian, and you formulate this KKT system equation, and now you can see this was our Q, this is the Jacobian of the equality constraint, and now we have this new guy associated to the value function. So this is the sub problem we solve every time. So we solve a problem like this, we move backward in time, we solve another problem like this, and so on until you get to the initial state. So that's how it works, dynamic programming, and that's the backward pass, the so-called backward pass in DDP. Now, DDP, they assume feasibility, so this guy is 0. F actually, F bar is actually all this guy here when you compute it. At convergence is 0, but during optimization, it is not 0 through the iteration of the optimizer. So this is the KKT system equation. Now, if we, I don't know what happened here, duplicated. So now we can condense this system equation and compute some feedback gain like this. maybe there wasn't a slide that I'm missing because it's not explaining, but never mind. So when you condense, I'm gonna explain that. When you condense this system of equation here, you will get this action value function Q. And then you invert only that QU to compute delta U as a function of delta H. So you compute a policy. DDP computes policy, not, yeah, also trajectories, but it computes local policy. It is not true that always trajectory optimization compute trajectories. You can also compute local policy. So it's an argument I have heard sometime, but you can also compute a policy because this is a feedback term and this is your feed-forward action. Yes, locally. Now, is a problem where linear, so dynamics linear cos quadratic, that will be a global policy. Just a caveat. But so, and in a multiple shooting, what you're doing is you're computing action like this, and you keep some infeasibility in the dynamics. As I said before, a derivative here and a derivative here is much better than, I mean, if I compute a derivative here, but then I do a shoot, so I need to use a derivative here. You see that there's a gap, and that derivative won't be as if I use it here. That's why multiple shooting is much stronger, and that's what you should do. That's another argument I heard some time ago. Like, you know, for control perspective, you want feasibility. Yeah, it's correct, but this is an optimization problem you're solving. So it should not be. You should leverage what is good for optimizer and not for control. And actually, if it's good for optimizer, it tends to be good for control. That's a good thing. And then you apply a line search. Typically, you can do line search like this, or you can do a forward pass and nonlinear rollout in different ways. That's probably different ideas. And you can also see this paper from Patrick where they talk about multiple shooting. So, ultimate control is essential for solving model predictive control. So as you can see here, and is this block here. So it's that our optimal control, and then we have, I think you guys have developed similar things. So for the step planner as well. So yeah, the one good thing is you can compute feedback policies and then get rid of the hover controller, and actually works much better, the feedback policy. Now, how we solve formula MPC? We use the hybrid formuling. So we have hybrid dynamics, a set of modes, and then reset maps that move from one node to another. You can see the nodes as written in numbers there, 1, 2, 3, 4, and then between these modes, this dashed line represents a reset. Sometimes the reset is an identity, sometimes the reset is not an identity. It leads to what we call impulse dynamics. And how you can formulate this, in essence, you have some cost and then some hybrid dynamics, a number of nodes, modes P, and then some reset maps. And then the modes define where you are in contact or not. That's the main limitation we have currently, but we are working on solving that. So because if the assumption of you are in contact doesn't hold, then the MPC really explode. So you can, but the good thing is you can model many behaviors using hybrid dynamics in locomotion, but not only. So walking gaits, trotting gaits, pacing, etc. And even this tiny guy walking. And these are videos done by James with Caracal some time ago. Now James has built his own Caracal, let's say. This was with Nadia in simulation in Python. And you can see, but the point here is you can see you can optimize many things quite fast. Yeah. Now I'm gonna go to handling endpoint constraint. This project was paid by a company, TCS. It's called Data Consulting Services. What they want to do is they want a quadruped that goes in a mine, and you keep the R in a given position. What we decide to handle some endpoint constraint. So you have this is the same perspective pipeline framework that I just showed before. So you plan some footsteps, you send mixing integer by the way, and then you have an MPC that follows given reference trajectory of an effector.
So are these steps predefined or it's optimized together in the?
No, they are optimized. So what I didn't explain more about it, but so you see that there are like convex holes in the region. So what this does is we take an elevation map. Well, in this example, no, but in the real robot, what we do is we take the elevation map, we compute holes, regions where we can make a footstep. We run a mid-size integer all real time. The mid-size integer used as a heuristic or as a kind of regularization, the math driver heuristic. So given a joystick velocity, we compute what it should be the footstep location. And then we have a mid-size integer that basically figure out what is the region where we should make a footstep. Once we figure out that region, we have, and that runs, if I'm not mistaken, like at 5 or 10 years. And then once we figure out that region, we have another planner. It's a quadratic program, by the way, that computes some Bezier curve that tries to reach your current footstep with the planned one, while also keeping within the region because you can push a little the robot. And this is also avoiding some obstacle, an effector obstacle, like when you walk in the stairs, you want to avoid the obstacle. And that's what we are running, plus some, to be honest, I don't know exactly how we are generating the effector trajectories. I know we were trying to do some area policy, but I think this video is not using area policy. And once we have all that reference, we pass that to the MPC. But what I want to talk here is about this endpoint constraint, how to handle. These have their own particular structure. So it's a constraint in the terminal node and only depending on the state. And what you can encode is like an effector pose, an effector twist, foot pose, foot twist, CRM position, whatever you want. Here, what we are doing is foot position and an effector position. So I want to talk about this just in a little. So also we can solve this type of problem. So here, what I only define is that where to land or where to put the hand, nothing else, no regularization, no trajectory, no planner that provides guess, nowhere starting. Very simple regularization. So it's when you put endpoint constraints, you kind of handle these problems much easily. If you try to do this with a quadratic penalty, it's like, good luck. You need to tune it really well. So those, don't remember, but maybe around 60 iterations it takes to 6-0. So yeah, so how we solve this endpoint constraint? So what you can see is that you can see this problem as a could be program that you have subject to some constraint, equality constraint, and I want to explain what that means. So W, it's actually the stacking of all the decision variables that we have in this problem. So H0, H1, H2, U0, U1, U2, and the multipliers associated to the constraint we have in each of the nodes. So W stack all this. And P is actually the endpoint Jacobian. And then you have A, capital A and A that actually are the endpoint constraints. So you can encapsulate all this in that format. And it's maybe not that obvious. It was not for us, at least, to figure out this. And what you can see is that the solution of this problem, this is the classical system that we have when we were talking about equality constraint. Compute the multiplier associated to the equality constraint using this short complement, B, A, and then all that. And then your endpoint solution is actually a combination of this plus this times 1, which is a multiplier associated to the endpoint constraint. And what you might think, well, A and B, they are so large. So doing this inversion are very expensive, but it turns out they have a structure and the matrices are very small. And that's all the trickery with it. But for now, I want just to tell you that DDP solved this. This is our DDP. So I will call it endpoint independent recaptive because we solve basically with a recaptive recursion. And then this is a endpoint dependent because depending on the multiplier, and it's a recaptive recursion as well. What you can observe is that to compute this guy, well, you have the inversion of A, and you have it here again, so you can reuse that, and a lot of the computation goes reduce it a lot. So so what in essence we do is we first run a recaptive recursion like the classical DDP. We compute this delta X, delta U, and then we do what we call this endpoint independent recaptive. So what we are computing is delta X, where X, this capital X and capital U are matrices that multiplies B beta, which is a multiplier of the point constraint. So in essence, it's a vector that, and then you sum up all this. So as I said, we reuse a matrix. I'm not explaining how. You can go through the paper, but yeah, it's very efficient and it's you can see also that works in real time. So you have here, so we are imposing point constraints in the feet and then the arm. So the robot moves terrible because there's no friction estimation, and I'm going to talk about that. So, but have a look, it works terribly. Because there's a lot of friction in the robot and then it's going down. So, and here when we do the same kind of circle, so you can see how it works. So what we're proving here is that works in real time, right? And then you can see the infeasibility, sometimes infeasibility grows and then quickly goes to 0. So, and you can also see in this plot, but yeah, the values are around few millimeters of error, so it's not that deep. And that concludes control. Now we move to estimation and the understanding part. So what is estimation is actually a dual problem. So, and what you have to do is you have some dynamics, you have some cost, and you want to figure out what is the parameters theta of your dynamics and some disturbances of it. Let me explain you with more carefully. So you want to find a set of disturbances and dynamical changes in the system. If you carry a payload, that's a dynamical change. And what you do is a Bayesian filter. You define belief. So I believe the state should be here with some covariance. I believe the disturbance should be 0 with some covariance, or I believe the parameter should be something with some covariance or some observation. So that depends on X, the state. Now, we have parameterized, we use still parameterized hybrid dynamics. And the set of observation just in practice is like AMI observation, linear acceleration, angular velocity, jog observation, velocity torques, visual odometry, ICP, all that you put in a Kalman filter will work. Yeah, but our goal with this project was not developing a Kalman, more advanced Kalman filter or localization problem, was actually the whole problem. Localization, dynamical understanding. So you have a robot, have a payload, you don't know, it estimates the payload properties, and also you grab an object and it estimates it quickly. Now, this video, because my student and I never agree, this video is not as impressive as it really is. He's displaying this estimation along the trajectory, but it actually takes like 4 iterations. And think about it, maybe an iteration should be like 10 milliseconds, so in 0.3 and 30 milliseconds, you've got estimated. But yeah, my student saw that it was not easy to see that, and he delayed everything, so it takes much more. So it should be powerful, but we haven't really implemented on a robot. So what was the innovation here? It was how to solve this problem very efficiently, exploiting inertial structure and full physical consistency in each iteration. And I'm going to talk a little about this. We did some work, some innovation here. So in terms of inertial estimation. So you have inertial parameter, those are the classical inertial parameter mass, center of mass, rotational inertia. You can express the rotational inertia in the center of mass in the point C using the parallel electron force theory, I think is the name. And when we say that these parameters are fully physical consistent, is when they make sense. And what it means make sense. Well, positive, the mass is positive. So a mass that is negative is nonsense, right? But same for the inertial term. So you need to define that the second moments of inertia are positive as well. So what you can do is you have your rotation inertia, you can decompose in their principal axis. These are called the principal components of inertia. And if you rotate them, you can actually get your second moment of inertia, which is related with second moments in probability because it's a kind of density function that we have here. That's a bit of the background. Now, what you need is this guy has to be always positive, or need to be positive to make sense in real life. And handling this is actually a beauty. There's a beauty and complexity as well. So there are two ways you can handle it using a Log-Cholesky parameterization. That's what Patrick Wensi proposed with someone else. And then an exponential value, that's what we propose. And I don't know why, but I get rid of the Patrick Wensi paper. It's bad. Sorry. So, or it might be somewhere. But yeah, I'm not going to explain the parameterization of 1C because this presentation is too long. I typically spend some time. But our exponential eigenvalue parameterization is, you are doing eigenvalue decomposition, as I said, plus some rotation defined by P. And what you can do is build use Lie algebra. Rather than parameterizing, you use algebra. And in the Lie context, when you want to formulate an algebra, you have some manifold, some constraints, some geometry, and these are the manifold constraints. So the mass times its inversion is equal to 1. Yeah, it sounds silly, but this is how it's explained in the algebra. And then this diagonal second moment of inertia multiplied by the inverse should be an identity vector. And the rotation times the inverse of the rotation, so the transpose of the rotation is identity. This third one is actually, as you can see, this is the spatial orthogonal group, and we can use the Lie algebra developed by that. So what the Lie algebra allows of is to move from a tangent space to a manifold, and then allow for in practice to optimize in the tangent space. So the tangent space is defined by P. Remember, theta is the parameter we want to find, but P is the tangent space. And this P is defined by this set of parameters. And what we can do is when we do something like the plus operation, we do an exponential map. So we grab all these in the manifold, or vice versa. When we do minus, we do a logarithmic map. So we go from the manifold to the tangent space. So this is how Lie algebra works. And the beauty is that with the Lie algebra, we can always ensure that the parameters are fully physically consistent. Why we need to do that? Is because if the parameters are not fully physically consistent, the mass matrix is not positively defined. And if the mass matrix is not positively defined, some of the algorithms we use for computing analytical derivative of rigid body dynamics doesn't work because they assume a real mass. That won't be a real mass. So, and having a Lie algebra, I think it's also when you can build it. Sometimes you can. When you can build it, it's much nicer than adding constraints. Like in the context of plotting like adding a quaternion constraint, I think it's better to work with Lie algebra and tangential rather than having quaternion constraints. Some people do that. So, but what is the problem? So having a Lie algebra is a nice feature. It's not highly nonlinear. The Wensi approach is highly nonlinear, but it has something that is not good. It's not singularity free. But no problem. There's other ways to solve this. So we will see. what I mean with singularity free is that if you have a rotational tensor and then the moment in x is equal to the the value in the moment in x is equal to the y, so you are in one of these axes, so you are in this kind of you are in kind of you are in the middle where there's singularity. And when there is this singularity, obviously there are problems. But this is an example of a case where we identify this sphere. It's actually singular. There's singularity, but we handle with null space parameterization, and I'm not explaining this. But what I really show is that if you use the method of Wente log Cholesky, because it's highly nonlinear, it tends to converge slower than the method we develop, which is the exponential eigenvalue. So the solution was not to do a nice parameterization like Wente did. The solution was to go back to optimization and combine things, ideas. So, the better solution, I would say. Just a tiny pitch. So a lot of people do localization with kinematics, so factograph, doesn't matter. And because these are perception folks, and they want probably to solve an exam problem all the time, and they don't really care about localization. And then you have a control guy, you say, please give me a localization algorithm, good. And they say, okay, it's too boring, I'm gonna give you something decent. Okay, they don't do so much before, because they don't care literally, this perception guy. But when you use kinematics, you are not able to predict motion like this for obvious reason. You don't have dynamics. And why this is important? A perception I would say, but you can close the drift with a stereoscopic sensor. But in agile maneuvers, you might not have any stereoscopic information when you're jumping. And you can find errors like this. Actually, in my experiment with MPC with this robot jumping, I have to use Vicon, the only one. And I was using the anybody's Kalman filter. So it's not a matter of how quality is implemented the Kalman filter. It's just assumptions that are not good. Now, when you handle dynamics, optimization is complex. You need to do in real time. Perception guys, they focus on fusion, we focus on optimization, and we are actually doing the opposite they do. Complementing what they do. And yeah, so we have developed an algorithm that can run in real time. And you can see some errors here. Okay, I'm going to start talking about simulation and our system ID 4, which might be important for you. And so in Crocodile, never talk about the hydrodynamics in detail, and I'm going to take some time. So you can model bilateral contacts or closed-loop kinematics through a quality constraint and using the Gauss principle of least constraint. And basically, so what Gauss says is unique. The constraint acceleration A is the one that's closest to the free acceleration of the system, subject to this kind of matrix. It's actually a Riemannian matrix. So now you have constraint like this, equality constraint like this, C for bilateral contacts, and K is for closed loop mechanism. Now, bilateral contact is something we did so much time ago. It's not that funny to explain this again. So I'm gonna explain more about the closed loop mechanics, which actually have Jacobian that might depend on B. And actually, this is a QP problem, can be solved with OD. Voila, again. So these are the type of optimization we are doing. So we are optimizing motion with Kangaroo. Why Kangaroo? We don't have Kangaroo, but we thought it was a very hard robot. Those people in Barcelona were crazy. Maybe Alberto can comment about it, but for me, I control a system, for me, it's crazy. So Kangaroo have, if I'm not mistaken, have three 4-bar mechanisms all in tandem. So you see in orange, green, and magenta. So we put in different blue. So actually four, we put these, or three are in tandem and one is not in tandem, sorry, the magenta is not in tandem. So I'm not a hardware guy, but this was done by my student. But we have noticed that the tandem for bar brings a lot of challenges to simulate this system and optimize. We are actually optimizing controls on this system. And when we use one single bar, it's easy. But when we do something like this, it's way complicated. So you can notice, I don't know if you can notice from there, but how it's moving the mechanism here, also this guy here, all the art, I mean, all colored is we are simulating. It's not just I'm optimizing the motion with Crocodile. So one of the challenges we also notice is when you have four bars, well, it's easy to get conditional matrices because this mechanism has a small masses compared with the masses of the robot. Often it's like that, often the way it's designed the robot. And then having robust numerical method is really important. So, and in this, we're exploiting this conditioning through ODIN, but also multiple shooting through what I explained before. So now, but I don't want to talk about so much control. I want to talk about much about estimation, where I think there's a good justification. Just to mention just a little, if we see the kinetic condition of ODIN for that problem is something like this. You got the mass matrix here, you got the Jacobian of the constraints, and you got the kinematic acceleration, and then H minus tau is the input commands, and H is the Coriolis and gravity, etc., etc. And yeah, so that's and you can apply. Obviously, we are doing optimization. We need to apply to differentiate the system of equation. We apply the implicit function theory, and it's something like that. And it's very similar to what I did in Crocodile, but now with some regularization terms. So what you can see is that right vector can be computed by using analytical derivative of inverse dynamics and kinematic derivative, but it's not that straightforward, and some math is needed. And sorry, the math is coming. So we have a closed loop mechanism like that. As you can see there, we're depicted. And we want to take advantage of the kinematic induced structure. So it means we want to compute this efficiently. You can formulate the closed loop kinematics in different ways. One way is by breaking in the middle of the bar, or one way is in the joint. So you can see that in this case here, you are preserving the number of degrees of freedom. So you have 4 theta's, and here you have 3 theta's. And then here the number of constraints is position plus rotation, and here is just position. So therefore, this is much better. But yeah, there are different ways of doing depending on how you want to do. And your goal is to ensure that the frame F1 and F2 are aligned together. So in that way, you close the kinematics. So you can see this as a position level. So it's a kind of logarithmic math over the spatial Euclidean group. We don't do position level. We do either velocity or acceleration level. And that's because you remember, so we are working here in acceleration. We're optimizing acceleration. So this is an acceleration level constraint. But when we have impulses, we do at velocity. Now, so there's a bit of algebra here, but when you do the derivative of this, can be seen as a spatial vector. You have to pick one body. We pick body 1, let's say. And then this is the spatial velocity of the body 2 expressed in 2, and you want to map it in body 1 coordinates. So that's a spatial algebra. And then for the acceleration, it's more or less the same. So you have the acceleration of the body, then you do time the differentiation over this, you get acceleration, and then you need to do the time differentiation over this action, which leads to this equation. And this is a formula that is actually demonstrated in the Roy-Featherstone book, but I'm not really going through. Then this can be rewritten as a spatial velocity expressed in in the one coordinate, in the body one coordinate, and then this times this, because these are a cross product, so it's zero, right? So that's why we are getting rid of that. So with that, we can bring the Jacobians and the derivative. So actually, we can do the differentiation over that. Maybe I'm gonna skip, it's too much material, but you can go through this paper. I mean, this paper, they do acceleration level. It's not explaining a velocity. I think velocity is easier to understand. I'm conscious of time and I want to stop explaining this. So, but it requires some knowledge on the algebra, spatial algebra, sorry. So something similar you need to do with inverse dynamics. You can rely on the RNA derivative, but you still need to compute this guy here. I'm gonna skip this. But we can discuss later if you are more interested. Now, the problem we really want to solve is in estimating friction. We strongly believe that friction is appearing here. We have noticed in our big one robot. This is the real problem we want to solve. So we model the forward mechanism, as you can see here, and these are some evidence that what I'm claiming. So when you change in the top, you see a 4-bar. We are moving the 4-bar, and we put the friction in that bar. You see how the friction is changing. So you have the input friction, which remains constant, but the output friction changes. So the output is the friction what you see. And we have noticed something like that as well. So that is I mean, typically you maybe don't want to do control with 4-bar because you have defining a fixed axis of rotation, not like Nadia, but typically you design a robot like this. But when you do estimation and you are not able to take all this out and then put in a bench, and then like in our case, you really need to model this. So, but also we are not assuming even localization. We want to run some experiment on the robot, collect data, and estimate all these properties, masses, all the things that I mentioned, and also friction. And also the disturbance. But we realize that the disturbance is actually tricky because we are ensuring constraints at velocity or acceleration level. And it means that if we break just once the constraint during the simulation, it keeps drifting. So we need to keep this kinematic consistency. So it means that when we compute disturbances to do the localization problem, we need to ensure that they are aware of the closed loop kinematics. So the way we do is we use a dynamic consistent projector M. So we project any disturbance into let's say kinematic consistency. So this ensures that you will be always in the null space, I mean, of the closed loop constraint. And then because we have measurements, so we will also map this covariance doing like this. And where the projector is this equation here, you can see from when you compute the equation. And basically, our optimization changes in this way. So we are embedding this NQ. And computing this is easy. The problem is the analytical derivative, which I'm skipping because it's too complex to explain. And now you can see some disturbances how we handle. Sometimes you see like a jump into like here, you see this jump. Yeah. So okay. So let me talk about the friction model. So we want to capture as much as possible. So one model that everybody knows is a long friction. So it's that region like this, and then you have the viscous friction. So and then you have the Street-Beck effects. And when you combine all of them, you get things like here, like this type of friction model. So now they are generally non-differentiable, non-smooth. We come up we use a model that is differentiable as smooth, because we do all gradient-based optimization. So, this is the model we use. This is basically representing a frictional torque, with this parameter gamma mass that you can see, and you can have an idea by changing the gamma how things change for the case of Coulomb plus visco friction, Seebeck, and all of them. But we need to ensure they are fully resistant. So it means that they always oppose, otherwise it's not a friction model, it's not a dissipative process. So, and the way to ensure this is by this constraint here. So they have to be positively defined, and which these are simple to handle. I will show you a minute, and then you have this kind of relationship. Why this is simple to handle? Because we can do exponential maps as we did before. So we like exponential maps. This is through our modeling solver. So we keep consistency. I mean, we use the constraint solver when we need it, when there's not a choice. Here there's a choice, because in our experience, that is the best numerical result. Another thing that we have is energy. So, and we have a constraint solver, by the way. So we have a energy-based observation. So you want to leverage energy, really, it's really important when you do friction estimation. So if you don't leverage energy, you can see that it's very hard to identify that friction. And when you start leveraging energy, now the identification starts to be much nicer. And how you typically do is because you cannot measure energy, you typically write this in terms of observation power and as observation. So this observation blue that you have seen here, and this is actually a balance of energy, where T is the total mechanical energy, contains kinetic and potential, and where the yellow is actually the dissipative friction energy, the dissipation energy that you come from friction. But we can analytically compute this. Computing the derivative for with respect to theta kind of straightforward, because in rigid body dynamics there are kinetic and potential regressors, like this joint torque regressor that James was using, and they can be written in that way. So you can see that it's very trivial to compute the derivative with respect to theta. But computing the derivative with respect, particularly the kinematic term, I mean the analytical derivative with respect to Q and B, it's a bit complex. And this is the equation here. It took a while to get it, but where this is the special velocity, and yeah, so I'm gonna skip that. But so some results. So this is the robot. You can see how it starting working much better. It's not yet perfect, but our robot is broken. So you can see unit 3 is very nice when you want to order a piece. So every time a leaf in the UK is horrible. So the communication with them, and you can see a kind of tracking. So when we fix the robot, we will improve this result. So now coming to contact physics. Why we want to do contact physics? Because we want a content implicit MPC, and we start developing a simulator first. So contact physics can be are actually posed as a complex programs, and that's the reason why ODIN is so fundamental for us to get it right. And what typically we do is we follow the maximum dissipation principle by John Morad. This is the paper you want to see. So basically, it reflects that principle reflects the dissipative nature of impact and frictional sliding. You have dissipation when you are sliding. When you are in a sticking condition, there's no dissipation. Something that I learned with this project. And they can be cast as a quadratic or second order comp program. For now, we are thinking about, we just implement quadratic programs formulation. But I'm going to explain with the second order comp program because it's the way that typically is explained. So the maximum dissipation, on constraint maximum dissipation principle is something like that. You want to compute that forces. So get to the De La Rose matrix is this term here. and subject to some free velocity in the contact space. So you map to the Jacobian. And typically, your constraint is typically you assume only Coulomb law for drive friction. And all the friction models I just explained, they don't use it, no simulator. So this is something I really want to at some point address. But for now, we are also in the Coulomb world. So why Coulomb? Because if with Coulomb, this is a complex program. If you use those other, probably it's a kind of NLP. So we're more complicated to solve. And this notation is probably kind of weird, but it's the notation you use in generalized inequalities. And basically you're saying that lambda belongs to the friction comb. A friction comb is a set where your normal forces are positive and then your tangential forces guarantee the Coulomb model. So if you linearize the comb, you get this. You get linear constraints. They are not anymore conic constraints, and then it becomes a quadratic program. And then seniority is actually the condition that ensures unilaterality. So basically saying, if I am in contact, my force should be positive. If I am not in contact, then my sign distance or this approximation of the sign distance function C should be positive. And I have a mistake in my line. This is possible. This is the other way around. Sorry. Yeah. So I'm gonna focus on the sliding condition because you don't believe it, but even Muyoko is doing wrong. So Muyoko formulate this as a conic program, and actually I'm not claiming that it's wrong. Actually, there is a paper that explains that. So. Conic programs like Muyoko solve, they don't preserve the seniority condition. When the contact is sliding, okay, you use Muyoko, you do your policy, you probably don't care about sliding. You want a robot that doesn't slide, but the simulator is wrong. So why? Because when you see the complementarity condition, you get something like this. So this is the velocity. As I was saying, this is the force, and then you have for the tangential. And now if you apply the maximum dissipation principle, which is this formula here, derived by this guy, you get that complementary condition. Basically renders, there's again error here, renders this complementarity slightly like this. And you can see this is different to this yellow is different to that yellow. By the way, this is a reference that you use when you want compliant contacts. So for region, we can assume they are 0. So Muyoko is doing that. So Muyoko is wrong. We initially were doing that wrongly as well. And I want to show you how that means. So you have this cube here, you are pushing, at some point you break the condition, and then you see you are not meeting any more seniority. So the box is jumping. So again, we have a force that is pushing, move from first the cube is in a sticking condition until the force is too big, then it starts to slide, but when it slides, we are not meeting anymore the single seniority condition, and then it's producing this type of jump. Now, so this asset, French guy, so in 98, already understood this problem in 98. And the paper is so difficult to understand, but in short, this asset basically, you probably can spot out that there was a third of this term here. And this asset, what you can do is like inject that correction term here in such a way you account for it. And now you don't know sigma because you don't know the force, but you can use the sigma that your previous simulation got, and then you compute, and then that's the way that you can implement it numerically. So it's not perfect, but as you can see, it gets rid of that behavior. So same problem as before. Now some forces start sliding, and there's not any more violation of the seniority condition. So simulation is a field that is a bunch of assumptions, and people call it into real gap. But and it's a field that is also there's some opportunity to do research. And actually, we are building a package called Genesys, not the other Genesys guy, American guy that are doing generative AI for simulation. We are building a simulator, it's referring to them, but it's funny, we picked the same name. Maybe it's with, yeah, there's a difference with why, but never mind. So this is insurance the seniority condition. Now, we can solve simulation with Odin and also with Gurobi. So the Genesys is not maybe with Odin, but Odin is really accelerating our simulation. And let me show you some experiments. So if you linearize the cone, you can write the conic constraint in that format. So that's the linearized friction cone. And you can solve this either with Gurobi or either with Genesys, with Odin. And here you have, when you solve with Odin, it's saying in the beginning, in that experiment that I showed, most of the time, the iterations are 1. So that is amazing. And it's because the Odin capability of water starting. Now, if I take Gurobi, it's always 14 iterations. So yeah, you can see an example that water starting is really important. It's not something like, nice to have. So yeah, that will accelerate way more computation, not only for a simulator, but for any solver, anything you develop on top of Odin. So here are more examples of things that we can simulate. So we can, these two are actually complex simulation because we have e-conditioned mass battery. So if I'm not mistaken, this is 1 ton and this is 1 gram. And same for the big and small sphere. So it makes simulation very challenging. And if you use something like Gauss-Seidel approaches, like also I think Muyoko implement, or racing that use a kind of Gauss-Seidel approach, probably they will explode. I haven't tested. You can also simulate in a quadruped, like we are throwing a quadruped, we just put a simple PD controller, and you can see that they are sticking. So this is sticking, this is sliding. Also, the sphere are rolling. You can see some rolling of the sphere. Yeah, and this comes to my end of my presentation. So I really thank you to bear with me in this journey. And this is more for the people that really like AI. So differentiation of QP is fundamental. In many applications, we just show when you have a simulator and you want to do trajectory optimization, you need to get the derivative, you need to differentiate the QP because the simulator is a QP. So this is a kind of bi-level optimization, but it's also important for deep learning. And now, imagine you have this QP parameterized by theta, and you don't know the theta. And what you do is you throw a bunch of data, your data set, and somehow this data set converts in some QCB or a combination, or some of them, a few of them, and then you have an output that comes from solving that optimization problem. That output gives you the solution of the QP, but also the multipliers. Now, the multipliers can make sense if you are, for example, learning the physics dynamic. We are not doing this right now, but I really want to do that. So because the multiplier are forces, and if you measure forces, you can build a loss function that depends on the multiplier, for example. So the loss function is the metric you want to minimize in deep learning, and that all this blue stuff is the forward pass. And then because you use reverse mode derivative, you are going backward in terms of derivative. So and you compute the derivative undifferentiable. QP is the problem of computing this guy here. And yeah, this is differentiable. And you can add many layers. NLPs, CNS, whatever you do. So and that's how it works in learning in general, right? And this paper from Brandon Amos and Sequel Porter, they actually implement the first differentiable QP, but it's full of assumptions, although it's super highly cited, like 1.5K from 2017. We implement that, and also we implement that paper, that method of doing the derivative, and we have another one that I don't explain today. But I'm gonna explain the basics of differentiable QP, differentiating a QP or OD. So you have a, reverse mode with the engine of backpropagation. What you want to do is to compute the derivative of the loss function with respect to your parameter, and you do kind of chain of rule here. And so you can write where you use the solution in case of optimization. You can use the implicit function theorem if your solver has converged. It's important, this aspect. You can compute delta U with respect to delta theta, and this J is actually the KKT matrix of our QP solver. Then you have B, which is a vector you want to compute in such a way you can do your reverse mode derivative. And the beauty thing in Brandon Amos is that when he developed this, he said, look, we rely on J inverse, but when we do the forwards, when we compute the solver, you already did it. Let's reuse it, and we can scale it. And these are the gradients that come from the gradients that come from your backward function in your layer, right? So, and these are some derivatives. So, and with that you can compute. I'm not explaining so much, but with that you can compute the derivative with respect to the parameters Q, B, C, the derivative of the QP. And what I did for fun, actually inspired by Brandon Amos, is so we implement a toys problem where we learn Sudoku. Sudoku is fundamentally a constraint satisfaction problem. It can be modeled as a binary integer program. So you have binary values, and your task is basically for each cell defined by A and J, you want just one K digit. And when that happens, you assign 1, otherwise you assign 0. So you have binary decision variables. And then you can impose all equality constraint that saying 1 digit per row. And so it's like this, where this is the row, and 1 digit per column, and also 1 digit per block. So this is actually a 3x3 Sudoku. It's a classical Sudoku we play, and where you have this block here. So but Sudoku can be 2x2, etc. And the task is basically given the givens, this set of number, to figure out the Sudoku game. So to figure out the remaining root numbers, and you can do this with this binary problem. Now, it's a binary integer program, but when you relax, it can be solved as a linear program. Relaxation, what it means, when you relax the binary constraints, rather than taking the value of 0, 1, you say, well, the value is between 0 and 1. And if you do that, you have a linear program, and actually this thing that is a solution our solver generates, not me doing that. So it's through a linear program that is solved with a QP program, as you were asking. Now, the way there are there are a few different ways to learn Sudoku. The way that we implement is we want to learn A and B, and giving a bunch of data set of games. So our inputs are the C. So C is the one-shot encoding of the Sudoku problem, and the output, and you got that output. So when you want to basically minimize your loss function, is the mean square error of the prediction. So you want to ensure you are predicting, you are playing well, let's say, playing nicely. Now, so when we implement let's say, the way of Brandon Amos is doing with our solver, you can see that you are learning. You go with Sudoku, so because this is the error, in about 400 epochs. And this is the evolution of the loss function. Now, when we do different derivatives, which are not explaining, because we haven't really, there's still a bit preliminary result, let's put it that way. So we can learn the same Sudoku in just 60 epochs. So the way we do derivative is fundamentally different. So we are stopping at some point the QP, giving the derivative rather than waiting all the QP solution about. And because the assumption, I think the explanation here, again, this is a preliminary. So the explanation is that so at the beginning, you don't really need precise derivative. You need informative derivative. And you see here, there's a bunch of epochs around 100 where we don't do so much progress. Instead, when we have more informative derivative, even in almost in a half of that, we solve them. And so again, the error is 0. So it means that we are always doing well Sudoku. We learn Sudoku perfectly. This it has been integrating Odin with PyTorch, all in the same package. And yeah, this what are the things we are missing is to deploy Odin in a GPU. So to scale to solve more complex problems, not this toy. But yeah, that's future research. And yeah, so you have here the comparison of these two. And that's ends my presentation. I thank you. I hope it was useful.
What I think we do then, folks, is because we have run over time by a couple of minutes. If you want to stay and have questions, please do. But otherwise, feel free to get back to your stuff. If so, I just had like a very general question, Carlos. Like, so you've developed this Odin solver, and it can apply in many different situations. And it's control estimation, learning, and so on. Like, what do you, by having a solver so general, what are you giving up in the specific cases? Are you giving up speed in terms of control and estimation? Things like that, because I know you showed us conversion speed, but so for example, for an MPC, you want to solve a problem very coarsely, but very quickly. So what are you giving up by trying to be so general?
Yeah, I think it's a good question. Because my background is robotics, and I'm aware of that. So currently we have a dense and sparse backend. But a lot of time, what we want to do, rather than using a sparse backend, is to use a dense backend by exploiting the structure. Let me put you an example in simulation. We haven't developed, but we thought about it. When you solve, for example, in soft simulation, a lot of people, they don't use a Cholesky solver, but they do some like kind of project gradients. So it's an iterative solver, not an exact solver for linear algebra. And in my way of thinking, it's a kind of backend. So now, Odin has been developed in a way that people can develop their own backend. We cannot do that for all applications. We do for the application we care. But it's possible to develop your own backend. So when you solve, for example, that's a problem that is more familiar to us. When you solve this, when you solve this type of holonomy and non-holonomy constraint like bilateral contacts, your mass matrix has some structure, same your Jacobian, depending on the kinematic induced structure of your robot. And rigid body algorithms come with methods to invert this mass matrix or computing the short complement, so Jacobian time mass inverse time Jacobian transpose, in ways that are efficient. And when we factorize our solver, we are actually doing those type of operations. So at the moment, we are not exploiting this. I just have to emphasize that. But OD has been developed, so then in a second stage, or when our simulator is all great, our focus is in differentiable, making differentiable the simulator, just to be more precise. But then we can leverage those rigid body algorithms so we can build our own backend. In that way, by providing access to the user to develop their own backends, you can exploit the structure of your problem as you think is best. Rather than implementing an optimization algorithm in DDP in a simulator, in the like people is doing. That's what it's doing. People in DDP, I was one of that. But also in simulation, they implement their own solver. Rather, I think the best way is to develop, the optimizer, make it great, and then acknowledge the fact that you want a specific backend and provide access to the user to that backend. So when you develop a simulator, you just specialize the backend.
I guess a good example of a solver that we've been using for a long time, it is super customized, is the QP that we use in the whole body controller, where it's like, yeah, this only works if you have a completely simple active set of constraints where they're all 100% independent. And that's how it gets its speed out of it. Do you think that, the problem is it's not really reusable to a lot of other things. The solver isn't super reusable to a lot of other things. Because it's pretty uncommon for all of your inequality strains to be completely independent. So.
Yeah. So our solver, just as a reference, our solver at the time being is written in Python, it's written in C++. Our Python will be integrated in JAX because we want to accelerate GPUs. Our C++ and also Python binding support working with 64 bits and 32 bits floating point. Same like I did for Crocodile. And it's partially co-generated. So you can co-generate, but it's under some condition it's not working well. And I know what is it. I know how to fix it, it's just a habit. But in future, let's say it's gonna be co-generated. So you can co-generate the algorithm of the QP. In some circumstances, might be more, might speed of computation as well, depending on your problem. There's not a one rule of thumb here, depending on the dimension of the system and so on and so forth. But yeah, in future, it will be also co-generated and co-generated from Python. That's how it's done at the moment. It's just it's still a bit buggy. And our plan is to develop a second order comp program because we want to develop the right physics, maybe an NLP, because we want to develop even more right. I'm very interested to model friction, not just with Coulomb in a simulator, but at least with Viscous. I think I talked with you some time ago, Robert, you remember, that I don't like that all simulators model friction using the Coulomb, but I would like to model also viscous friction and at least the viscous friction, and I think it might be useful. But that will require NLP, as far as I understand. So we will, but the basic idea can be extrapolated to other contexts, so not just QP. Now we learn how to develop really advanced QP. Now we just need to wrap up this project and move to the next solver.
What do you think the future of like really advanced physics engines is? Seems like almost the speed of the physics engine is now being a little shown to be more important than the accuracy in all this RL stuff that folks are doing.
I mean, in the context of model-based, you want to have a better simulator. In the context of RL, you do seem to real and foggy. But I think I assume if you have a better dynamic, you rely less on sim to real, and maybe the solutions are more specialized and less just kind of average. Maybe can be better now. All people is focusing on scaling the simulator, but it doesn't mean we don't want to scale. It's just we are focusing. If we can scale OD, maybe we can easily scale That's the example what I'm saying. We want to have auditing a GPU, and then when we have to auditing a GPU, what next for a simulator? Well, we need to have the rigid body dynamics written in GPU. So we'll need to make a decision of maybe by Pinocchio. We are using Pinocchio, but Pinocchio, if they don't support GPU, and at some point we want to have GPU, probably we'll need to write our rigid body dynamics in Python with, I will say, is the best way to do through JAX, but maybe I'm open to hear. We haven't really decided, but I think JAX is the pretty handy way of doing.
Isn't what's the name of the guy? He's in New York.
Ludovic Rigetti.
No, the other one who's at the university that doesn't have a PhD program. Yeah, he has an implementation of physics in GPU already.
I didn't know. I know he implements some linear algebra solvers in GPU.
I think, yeah.
You mean rigid body dynamics? The work that he did during his PhD with Scott.
I have no idea. But I know that he was using it in his GPU MPC algorithm. He was using their rigid body dynamics.
Yeah, Brian.
So I was saying, like, you could look at that.
Yeah, Brian is a good friend. I have chatted with him many times, not this year, but last year. Yeah, at the moment we are not on that need, but yeah, I could at some point considering anything Brian is doing. I hope he's progressing on that so I don't need to develop any.
Yeah.
That's it.
I'm not particularly excited to do that. Just.
But piggybacking on what Robert said, like one of my follow-up questions to you was going to be like, no doubt if you can make the simulator better, that's probably a good thing, all things considered. But when you gave the example of, say the robot just wanting to touch the floor but not exerting any contact force, it might be great to simulate that effect and behavior. But I feel like from a practical point of view on the robot, even if we wanted to specify that behavior, we wouldn't be able to control it.
Yeah.
And so I feel like, as opposed to maybe sometimes getting a better feed forward model, I feel like in a lot of practical cases, you just
I fully agree.
behavior.
I fully agree. Practically, it might not be important, but you can have other type of constraint join limit. So you are touching the endpoint or limits of the join, and then by not creating a reaction, or in general, maybe you can also say it might be another corner case, but in general, when you do embedded optimization layers in deep neural networks or deep graph, I prefer to use graph, but never mind. So you cannot really assume anything on that.
I think that's
We are thinking in Odin not just a solver for MPC or simulator, but maybe we want to solve those problems ourselves, and also some AI problem, but because we are so ubiquitous in many applications, we thought that if we provide a tool that is more general, a lot of more people will use it, more impact, research impact. That's what we are trying to achieve here. So we are trying to achieve that this paper gets cited in a few years, over 1,000. So like OSQP or those, I don't know if it's gonna happen, but that's what we will like to achieve. And that everybody use it. But for that you need to build something really good, not only mathematically, but a software that is useful. We already have a bunch notebook, so I can show you on notebooks that explain duality, explain a lot of concepts. So all these notebooks here, we are slowly creating.
Sorry.
Yeah. So this is actually the Sudoku. I was generating this to create the plots.
It's not on the screen.
Okay.
I
can show you in person.
Yeah. I guess it gets back to my question about specialized solvers for stuff. Don't get me wrong, like with the NPC stuff, one reason why you want it to be faster is so that you can run with a longer prediction horizon, right? And no doubt that's super important. But part of my interest with all like these sampling based NPCs or any NPC that's been put on the GPU, I would just love to run like an ensemble of 4 or 5 NPC instances that vary
So,
just in some system dynamics.
So
And I feel like that'd smudge out a ton of the sharpness
So-
that we see in NPC policies.
Yes.
I have a white paper with Robert. They are reviewing and it's about,
I confirmed they're reviewing it over the weekend, so.
I hope some positive, but I don't know. So I think you are talking about a slightly different problem in the way I see. So let me just try to phrase. So what is the problem with MPC is that you use deterministic dynamic and more importantly, you have deterministic policy. But you want to do a stochastic MPC. And typically when people talk about stochastic MPC, they refer to stochastic dynamics. But I don't mean only that, also stochastic policy. So you can build some ideas connecting a field is called variational inference with DDP. And that's all the white paper about we wrote for AI. And in practice, it's like a sampling based MPC with derivative, which should be more informative and converge faster. And if you see it from a sample perspective, it's like you have many recursive recursion runs in parallel with rolling out different stochastic policies and computing all the same for the forward pass. So you have some kind of gradient information. I think it's better than sampling. And the reason is when you do the sampling MPC, implementation wise, almost like, wow, this is so simple and works so well. But they rely a lot in sampling with the right distribution. Because it's a kind of Monte Carlo integration you do. When you have derivative, the derivative is telling you more or less when to sample. So that's why the derivative is informative. That's why if we develop something like that, it should be better than a sampling based MPC. Now it's much complex theoretically. And because you use nonlinear dynamics, I also think it might capture not unimodal distribution because it's like you linearize unimodal, but in a comprehensive thing, you might see like a multimodal. And you can probably capture multimodal things. And yeah, stochastic MPC can not necessarily have to be done with model. You can do differentiable MPC, differentiable stochastic, and then has an algorithm that learns everything. So yeah, so you rely a lot on how to sample. Maybe in many problems it's easy. It's saying that some people have cooked, but maybe it's not that easy for yeah. If you think about only locomotion, maybe, but you want a robot that locomotes, open a door, and blah 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 blah. So I don't know. No one has, but I would suspect there will be some problems with sampling based. And yeah, Robert is about connected variation inference with DDP. This is the idea.
What do you think?
And it shouldn't be that hard to develop. But we are developing a simulator. I think that what is harder is to develop the simulator. Once and all the other stuff, once we have all the stuff, we will be in a better position to develop that. Because you can do this sampling based. I could start implementing today, but I want to solve content implicit problem, and I don't want to solve just locomotion manipulation problem. So, like one of the benefits of doing this sampling from an MPC perspective, now you won't stock in local minima. So imagine and typically manipulation is a problem you have. You want to pick an object here, and you have a bunch of obstacles, and then if you find one, maybe the MPC is like, oh, I can't. But if you have some kind of randomness, because you have multi-recursive recursion and multi-forward passes running, at some point you will find a solution that brings you outside of the local minimum. So from an MPC perspective, it makes sense to do that. And also for a sampling perspective, as I explained before. So it's kind of embedding these two ideas together. And it's not discarding one and getting. Yeah, we are not discarding.
What do you think is like, what do you think is the future of like the computation platforms that you'd use for MPC? CPU, GPU?
I think when you do this kind of stochastic MPC, for sure GPU.
Yeah.
When you don't do stochastic, well, we will try to see. I'm not fully convinced that maybe a CPU is better. I don't know, SAT Manchester shows something different, but personally, I don't know, even I need to see with my eyes.
What?
So the AQR stuff, you guys, you have an Intel from SAC, right? I'm talking about that paper. The AQR with GPU, how has
I think it was really good, but it was also still, I would say that was purely a tracking controller.
Yeah,
And James and I talked about this a lot, and how one of the big differences between that and like Crocodile is that what your Crocodile is coming up with is you're not giving it necessarily a reference trajectory, it just kind of finds things.
Yeah.
Whereas the LQR controller from Zach, that was, you give it a reference and it tracks it, and it did very, very well, and that was impressive. But it wasn't like a
what was the frequency, by the way?
333 hertz.
I think it's achievable. I mean, it's as I mentioned to you, James, there's some more on parallelization. I started doing, but I stopped it.
I mean,
But I need to somehow.
You would say that a 333 hertz solver of a whole body MPC problem is feasible?
Yeah, I think it's possible, yes, but it doesn't mean that it's you know, bit wrong. It's not done in one day, but it's possible.
I was also gonna say there's the inverse aspect of that is it advisable? You're talking about some of these things, one of the nice things about some of the algorithms that you can just run slower is it's just less compute. Because, you know, if I'm increasing the amount of compute required to do something, I'm also increasing the amount of power that the computer is consuming. And from a practical, like long-term solution perspective, that's something that has to be considered.
Yeah, you're right. I don't know. I don't know about power consumption, especially with GPU.
Yeah.
If you put in a GPU, the power consumption.
Well, but there's some of these newer types of compute boards as well that aren't GPUs that are more customized for running like neural networks and things like that. That may be better and more efficient for some of this as well. I basically just said all I know about that.
I think it's, I don't know, I'm not familiar, but it doesn't look like it's not possible. I mean, first is the problem of how we parallelize, so the math, and then the problem of how we do this in that is not just fast, but also something that you are willing to put in a real robot.
And James and I have talked before as well about, you know, some of the dynamics, actual equations and solves that you're doing. Even if you're discretizing the solution at, you know, 10 milliseconds, which is pretty common, right?
Yeah.
Your dynamics aren't meaningfully changing at that type of time horizon. So you could almost like chunk your actual dynamic equation because you're linearizing the thing at the end of the day in order to solve it behind the scenes. And so if you just apply like the same set of rigid body dynamics for 5 time steps, and you're integrating, assuming that your deviation is still small angle approximation stuff.
Yes, yeah, so you know, Patrick has worked with this multiple resolution for sure. It's not something we do, but our research can complement, can help.
I mean, but an even cruder example of that is Zach's recent paper. Was it with the Google DeepMind folks of just getting there? Was it H1? I can't remember, to walk. And yeah, the walking did look a bit shitty, to be honest. But one of their things was like, right, instead of at every node, we'll take a linearization. We'll do it at every other node and just interpolate. So we're like half our derivative cost. Yeah, it's very crude.
But I also want to comment that computing the derivative and the linearization is not the problem for us. In Crocodile is actually the backward pass. So reducing the dimensionality of the backward pass and some node will be more beneficial than just computing some derivative, updating some of the derivative.
Yeah.
So if the backward pass the main bottleneck and parallelizing it will help a lot. Then comes forward path. Now that the derivative is the one that takes less. I know. Some time ago, Emma Thoreau say derivatives are expensive, but sure, you are doing non-diff. I mean, Emma was doing numerical differentiation.
Oh, yeah.
Yeah, of course. Numerical differentiation is really expensive and it can some kind like cubically or something like that with a dimension. So we don't do, if you do analytical derivative, it's not a problem, not a problem for us.
I do think, I know we've talked about it on Slack and I'm aware I've asked a ton of questions, so I'll leave it after this. But I know we've talked about it on Slack. I do think there's more work that could be done in how to tune the controller, how to tune an NPC controller to just get more realistic, like closed loop bandwidth. Because I think a lot of the problems of like an NPC having slip gains is because the closed loop bandwidth of the controller is really high. And a crude way to just get that out of the way would be to like put a higher weight on, say, joint velocity costs. Then that interferes with your tasks. And there's various other ways you can try and affect the bandwidth of the controller, but I don't think anyone's got like a really good handle on how to do that.
So I think at some point we need to embrace data. So that's why we want to do this different, what we did differentiable QP, and then the next step will be to improve it a bit more and then probably go into our MPC. So, but the differential MPC, as I said, have, you need probably to scale with GPU, and the problem is Pinocchio. So, hopefully someone will bring, or we will develop, never mind. So why differentiable MPC? Because you can inject data like we do with this Sudoku problem and learn. Rather than you tuning, you got some data, so you can clone a behavior, for example, or you can have an RL kind of policy that you, the RL is like tuning plus, I will define tuning like sending reference and weight to the cost function. So not just the cost, but also the reference. So you could have a RL policy that learns to produce data as an output, and you have an MPC on the bottom. So rather than having an end-to-end, why that could be beneficial, because now that the neural network is learning something high level, maybe it's smoother signals, easier to learn. I mean, when you do RL policy, how people learn? They learn joint position, because these are the smoothest signals you can get. And yeah, sure, universal function approximation neural network, but then you need a massive neural network to really achieve that dream. So practically what people do in RL is they learn signals that are smoother, and they don't learn torques because they are way jerky. Now, if you have high-level reference like a COM, it might be even much smoother, much easier to learn. This is, but yeah, you can also, as I said before, you can learn behavior. So imagine I'm doing some motion, record it. I want to clone that behavior in a robot, but my dynamics is different to that. How I do it, always through differential MPC. Yeah, you can use diffusion policy, right? And diffusion policy.
That's just a method, but that would act as a method